Good morning, all. I hope I'm audible for the guys who have joined me online. So, Puneet, Priyadarshini, if you can let me know, that'll be helpful.
Yes, sir, you're audible.
Okay. So, any questions from anyone? Let's start with questions.
How does the RF pulse create the phase coherence?
The RF pulse does not free the phase coherence. The phase coherence gets disturbed because the equilibrium condition is the decohered random phase state. RF pulse helps create phase coherence. That we will have to wait until maybe next class. Okay. Any other questions? Yes.
So, longitudinal relaxation time is larger than the transverse relaxation time.
That's once again because of the mechanisms that are involved, where the exchange between the surrounding is a little slower than the exchange that happens within spins. If I have to ask you, which distracts you more, a friend or a person who's sitting right next to you who speaks a lot when your class is going on, versus something what happens outside in some other classroom? Yeah, so the R2 relaxation is more like your focus is being destroyed. On the other hand, the full relaxation is more like something that happens outside. So the coupling between the spin and the lattice, let's put it in this way, is a little weaker than the coupling between the spin and the spin. Okay, so and therefore there is a difference in time. Okay. Okay. So good morning, everyone. Let's start today's class now that the doubts are out of the way. So let's quickly recollect what we understood thus far. For a spin-halved system, the two energy states are degenerate, which get split by gamma H cross B naught, being alpha being the lower state, beta being the higher energy state for gamma greater than 0. And we also try to understand or appreciate the fact that gamma and B naught both drive the energy difference. Gamma is an intrinsic quality for a given element. B naught is something that you have control over. So people try to have higher and higher magnetic fields to further separate them. But you're also able to understand from the delta P, which is P alpha minus P beta, that B naught plays lesser of a role while the concentration plays a big role. So in addition to gamma, B naught, you're also trying to emphasize on the natural abundance of a given isotope that you want to study. With this being the case, we also highlighted the fact that NMR is intrinsically insensitive because the population difference is rather small between the ground state and the excited state, resulting in a small polarization. And in the last two classes, we tried to understand how does this polarization come up. And to repeat some of these so that we can get up to speed. Yet again, if you have any questions, please unmute yourself and ask or raise your hand here. We looked at how the quantum magnet's orientation with respect to the main magnetic field does not go parallel or anti-parallel with B naught, but is at an angle. However, when you resolve the mutually orthogonal vectors, the longitudinal components add up for the alpha and beta. Since the population of alpha is greater than beta in the thermal equilibrium, you get a small net magnetization. That is, I see Puneet typing a message. I would rather appreciate if you speak up. So here you have a net bulk magnetization that comes up from the sample that is oriented along B naught. And therefore, we said all the information content is in this. And in yesterday's class, we said if you ended up disturbing it, because the rate of change of angular momentum, which is dj over dt, which yet again we will see in more in detail on how the RF pulse succeeds in erasing the B naught and getting the magnetization in the transverse plane. Since the cross product is 0, you cannot measure it. And if you want to measure it, you have to take it away from equilibrium. And that is achieved by an RF pulse, which ends up flipping the M naught into the transverse plane. The example that we took was a 90-degree flip angle where the magnetization flips to the y-axis. And importantly, we were also trying to understand how the pulse that is being applied results in something called a phase coherence, meaning that the random phase that existed in form of a cone actually bunches up together to have all the alpha spins and beta spins coherent in phase, and therefore resulting in net magnetization that's different from what you started off with. And with this, we were able to highlight a few important phenomena of how these magnetizations come up. The longitudinal magnetization comes up due to the population difference in alpha and beta states, and also due to the random phase, meaning that nothing exists in the transverse plane, everything is along the longitudinal axis, which is parallel to B naught, which is once again where we highlighted that this is where NMR could be looked at in a classical manner, where the quantum mechanical spins finally result in a net magnetization, which we are very familiar in exploiting to get whatever information we want from classical physics. On the other hand, we also highlighted that when RF pulse is applied and you've got cos phase coherence, you end up getting the magnetization away from thermal equilibrium. This is an example of a 90-degree pulse where the entire magnetization flips to the transverse plane. You could have any theta pulse where you could have gotten the M naught from equilibrium just to at a certain angle, theta. And all that power exists with you in terms of the RF pulse, which we will see when we are dealing that in detail. Since the mechanism of generating the longitudinal magnetization and transverse magnetizations are different, their return to their respective equilibrium also follows different paths or mechanisms. What do I mean by this? When you started off in thermal equilibrium, you have greater population and alpha state than the beta state. But when you ended up applying a 90-degree pulse, the populations become equal. You realize that the return of populations back to thermal equilibrium is what is going to help you recover the longitudinal magnetization. So that is one mechanism where the spin ends up coupling itself with the lattice to get the populations back. On the other hand, you once again realize is that the non-equilibrium state that we have generated has a phase coherence which did not exist in thermal equilibrium, and therefore the return of phase coherence to phase decoherent state on the transverse plane decides the rate at which the magnetization that you're detecting dies, as in the free induction decay. Where did we draw? There it is. If there were no decay, then you would have had an oscillation that keeps ringing all the time, which you could have measured, gotten its frequency. On the other hand, in the realistic scenario, dampening happens. This is not new. This is a similar phenomenon which you would have studied even when you're doing the pendulum experiment, where you'd have started at some point, dampening happens and the pendulum comes to a halt. And the halted state of the pendulum is the equilibrium state because that's when it has the lowest of energies. On the other hand, similarly for the spins here, you started in equilibrium state which had a longitudinal magnetization due to population difference and no transverse magnetization due to a random phase that exists in the XY axis or XY plane. After application of the pulse of 90 degrees, you equalize the population somehow and created a phase coherence, neither of which are equilibrium states, and it returns back. So each of this is associated with its respective transverse relaxation rate constant, which is called either the longitudinal relaxation or spin lattice relaxation for getting the recovery of the longitudinal magnetization, transverse relaxation or spin-spin relaxation for the phase coherence to get destroyed as a function of time. The time domain signal that we end up acquiring is Fourier transform in order to get a frequency domain spectrum, because generally we are more comfortable looking at the spectrum. We started off this class by trying to say proton NMR spectroscopy helps you pick up chemically different spins, for instance, chemically different protons. So therefore, chemical shift is what chemists are more interested about. Here we took an example of water, so therefore you get only one resonance. Hopefully we'll see today how when you have multiple spins that exist, the spectrum ends up coming up. And this was one of the questions that was asked today, why should T1 be greater than T2? This is a very general phenomenon that has been observed, where, now think about it, you created something from longitudinal magnetization. But let's say the opposite exists, meaning that T2 is greater than T1, just for the sake of induction, mathematical induction. Let's say T2 were greater than T1. Do you realize that the magnitude of the longitudinal magnetization plus the transverse magnetization should be a constant, because that's based on the initial population difference that existed. But if it were the case where T2 is greater than T1, you would realize the magnitude at some point would actually be higher than what it can be achieved. Does that make sense? Did you understand or you did not? So T2 relaxations says how quickly the M naught disappears from the XY axis. T1 relaxation says how quickly does M naught come back in the Z axis, and both happen simultaneously. If T2 were greater than T1, which means that the transverse relaxation rate is slower than the longitudinal recovery, remember that sum total of magnetization. So let's say you started with M naught square. M naught square should be equal to mx square plus my square plus mz square. Why am I saying this? You can imagine M naught also as a vector, which is mx I cap, my j cap, mz k cap. And therefore, the magnitude of this magnetization is going to be given as the square root of mx square plus my square plus mz square, where mx square plus my square is the transverse magnetization component, while mz square is mz is the longitudinal magnetization component. If, in the regular case, T1 is greater than T2, what is going to happen? You would have started off such that this is going to be m naught square, right, where this is going to be 0. So this conservation works. Let's take the equilibrium. In equilibrium, this would have been 0. This would have been m naught square. So the conservation works. But if it were the case where T2 is greater than T1, you would realize a situation where the sum total will be greater than m naught square. That does not make sense physically. Law of conservation of mass, here law of conservation of magnetization, you cannot create more than what you actually could have intrinsically. So that's why T1 is generally equal to or larger than T2. Very commonly, T1 is greater than T2. Very few times, you have few rare examples where T2 is very close to T1. Okay. Puneet, you had a question. Please unmute and ask.
Sir, so this bulk magnetization comes from the population difference. After applying 90-degree omnigenous pulse, population equalizes. So what's the effect of this equalization of population on the magnitude of the transverse magnetization?
You are confusing two different magnetization. Longitudinal magnetization comes from population difference. Transverse comes from phase coherence. The reason why the populations become equal, which I cannot go into detail right now, we'll probably see it in the subsequent class, which is on Tuesday, where we look at block equations more seriously, where the spin physics of how do we achieve this with the RF pulse will be discussed in detail. But before going to the mathematical rigor, I have realized that it's better that students understand the concept more holistically than going into the equations. And therefore, I'm spending more time this time here. So if I have to answer you right now, if you end up destroying B naught, do you realize the alpha state and beta state become degenerate?
Yes.
Yeah, that's kind of what happens when you're applying an on-resonance 90-degree pulse. You kind of virtually take the effect of B naught out. The moment the B naught effect gets out, this is not a direct explanation, but this is kind of how I'm able to convince you that the populations become equal.
So my question was like, okay, population becomes equal, but the equilibrium bulk magnetization was the because of the population difference. In after applying omnigenous pulse, population equalizes. So what's the effect on the magnitude of the magnetization?
That's what I'm trying to make you understand. The number of spins that would exist, there is a P alpha plus P beta that will be equal to 1. You started off with a condition where P alpha is greater than P beta. Remember that P alpha plus P beta is always a constant, and we can take these as fraction of population, therefore it should be equal to 1. Therefore, you're going to have 0.5 here, you're going to have 0.5 here, 0.5 of M naught, 0.5 of M naught, that's going to be bunched up so as to get the M naught along the transverse plane. Did that make sense?
Yes.
Yeah, this was like 0.501. Let's say this is 0.499. And therefore, you had a very small, tiny 0.002 equivalent of M naught here. That's the same M naught that's going to come up. You cannot create more than whatever you had to start with. That's the long and short of this.
Thank you.
Yeah. Any other questions from others? Please unmute and speak up. Else, I'm going to move on to the next set of topics. One of the mathematical topics that will be of help to us is the Fourier transformation. As the course is little tight and expected to have that knowledge of the background, I'm just going to quickly give you an idea of what happens when you Fourier transform a cost function. Let's say this is cos of omega naught t, then the Fourier transformation of this would be something like, this is just tentative that I'm drawing. The more clarity will come as we go forward. Okay. So when you, oh, actually this is wrong. So basically, when you have a cost function that you Fourier transform, you will end up getting Dirac delta functions at omega naught and minus omega naught. Slowly you will realize the zero will be set to something called a carrier, which all we will discuss in the next week on the next class. And similarly, if you end up doing the same thing for a sine function, it's going to be a bit difficult for me to draw on top of it. Remember, the sine function is going to be orthogonal to the cos function, meaning that it's phase shifted by 90 degrees. Wherever cos is zero, the sine will either be maximum or minimum, and vice versa. Whenever it when the maxima or minima are present for cos, the sine will be zero. So when you have the sine omega t function, when you end up Fourier transforming it, you yet again get a signal at omega naught, but the signal at minus omega naught will be inverted, meaning that if the intensity is 1, it will be 1 here. If the intensity is 1 here, it will be minus 1. And therefore, in general, we would end up taking a complex signal, which is cos omega naught t plus I sine omega naught t, to do something called a complex Fourier transformation. So this is going to be exp I omega naught t, which when you do a complex FT, complex Fourier transformation, you are going to get a signal such that at 0 and minus omega naught, you don't get any signal. At plus omega naught is where you get a Dirac delta function. Okay. The reason why I'm saying this is that quite commonly we'll be talking about the time domain signal and immediately inferring the frequency domain spectrum. And this is their correspondence between each other. If you have a time domain signal with omega naught t, then you're going to get a delta function at delta of omega naught plus delta of minus omega naught. This is the sine part, sorry, cos part. The sine part will be something like this. On the other hand, when you do a complex Fourier transformation, you're only going to get the frequency. Remember, your omega naught is what consists of gamma b naught. And why did we focus on gamma b naught? Because we realize that's what the magnetization has information. That's what we want to extract, which we'll see in a little bit of detail right now. Which is, let's take an example of methanol. We see that there are two different types of proton, the methyl proton and the hydroxyl proton. And here we are expected to get two different NMR signals. And therefore, what happens is that each of this has its own M naught associated. That's because they are in different chemical environments. We did refer to something like a chemical shift, which changes their local environment, which we'll see a little later. But let's try to understand based on whatever we have generated thus far. You're able to realize each of the spin is a different spin. So therefore, it's going to have its own alpha and beta states. The moment it has its own alpha and beta states, you're going to have a magnetization, bulk magnetization that comes up, which you can exploit. What do I mean by this? Is that it's going to have its own m naught. This is at a certain frequency. This is going to have its own m naught at a certain frequency, right? Of course, the m naught generated for methyl will be 3x because you have 3 protons equal. This is where the quantitation of NMR comes up. Okay, and therefore you're able to realize methyl protons are more sensitive than something like a methine proton. Okay, so because the number of identical protons are multiple, and therefore the signal just adds up. And the same set of parameters work. We can for now assume that you apply a 90-degree pulse, which is on resonance. We'll define this next class, where both of them come transverse. Remember, they have their own frequencies of oscillation. And how does that come up? Is because of local diamagnetic electron clouds. Electron cloud. Essentially, what we are trying to say is that you have a certain spin. It has its own electronic environment around it based on the chemical entities and the identities of the elements that it bonds with. There are some elements that equally share the electron in a covalent bond. There are some elements that pull it towards themselves. There are some that push it towards the other side. Therefore, the electron cloud is determining factor here, because remember, once you have a diamagnetic electron cloud, that also has its local magnetic fields being present. And in order to explain this, I got an AI generated image. Please don't take this literally. Instead of me drawing, I believe that this is still a better representation that will help me explain a little bit. I should also acknowledge proper sources. So I just gave a few prompts, which I hope help establish what's going on. The figure isn't great. There are mistakes in it, but let's try to understand. You have a main magnetic field B naught, and you have your sample here. And you have a given spin that's present, and you have the electron cloud around it, which is shown in the cyan cloud. And this is an example where you have a symmetric cloud distribution, and therefore there is a local B field that is being present, and the local B field also interferes with the main magnetic field. We are talking about magnetic fields, so these are all B's. You can think of a B local here, which interacts with B naught. We'll formalize it in a moment, but hopefully it makes you understand the nuclear spin, which has a magnetic moment due to a non-zero gamma and I, ends up having its own magnetic moment. Now it is in conflict of looking at multiple fields that's available to it. The local effect is going to be given by the electron cloud, but the major effect comes from the B naught, because the strength of B naught is so large that B naught drives the largest orientation, or the question of how the mu will orient with the main magnetic field with the B naught, and the local effects allow for differences that each spin experiences from the main B naught that's applied. So this is an exaggerated example. There's a small mistake here. I asked it to make for the same spin, which means that if the gamma and I and B naught are constant, the length of this vector cannot change. So this is where AI makes mistakes, so don't take this literally. The length of the vector should have been same as this, and you have the same length of vector, but I am happy about the electron cloud it ended up making. You realize this is a stark example where the electron cloud is not symmetrically distributed, and one can imagine there's a three-dimensional shape associated with it. So the magnetic environment that each spin experiences is dependent upon its neighbors, and it's a three-dimensional effect, and that is, so that is going to be, I'm sorry. So that is going to be given us such that the B field that's experienced, how should I, let's say B effective. I'm going to use the term B effective again later on. How do we write it? Let's say B experienced by the spin is going to be 1 minus sigma kk times B naught. This is the theoretical formulation that comes in where something called a shielding parameter is defined. And this is the static magnetic field. And if you closely observe, I put indices for this. Sigma is called the chemical shift tensor, which has multiple elements present in it. A tensor has very specific properties that comes in handy for us to treat these kind of systems. Essentially, it's a 3x3 matrix that defines the magnetic field as anisotropy. Let me repeat again, magnetic field anisotropy. What is meant by this? You need not have a homogeneous distribution of electrons around your spin. You could have an inhomogeneous distribution, and that parameter could be, in many cases, is anisotropic, meaning that its measurement across different axes is different. Rather than if you take a sphere and measure its radius from everywhere, it's going to be constant. Let's say you have a distorted sphere where there are differences that come up, the measurement would vary. Okay, and that is defined as this chemical shift tensor. And the chemical shift tensor is generally anisotropic in nature, meaning that the property when measured is going to be heterogeneous based on your measurement. But thankfully, when we measure isotropic, which is we only measure the isotropic component of this tensor, which comes up to be the average of the trace of this matrix. Meaning that since we are looking at solution state NMR, since tumbling happens all the time and it's in period of say nanoseconds or sub-nanoseconds, the reorientation of the molecule happens so fast that you cannot measure this anisotropy from chemical shift. And therefore, when you only end up measuring something called an isotropic chemical shift shielding, isotropic shielding parameter. So therefore, for now we can imagine in our case, you're going to have this substituted by one number. Therefore, every spin that is being present is going to experience its own local B field. Okay? So therefore, what this transpires into is that we started off by trying to say you applied B naught of K, but now you have to add this parameter onto it, where the shielding also comes into influence. And therefore, what is the main effect that is going to happen? For the sake of discussion, you started off with CH3OH. Let's try to label these with different colors. Let's say the methyl proton is in red, the hydroxyl proton in green. If there were no local B field effects, you would have had energy difference after subtending them in B naught would be equal between these two spins. But remember, the local chemical shift anisotropy changes this parameter, allowing for isotropic shielding parameter to be different for these based on the average electron cloud the spin experiences in solution state. And therefore, what essentially happens is that there could be changes to the energy difference. Of course, these are exaggerated. Why do I say these are exaggerated? The energy difference between these for a 11.74 Tesla is about 500 megahertz, and I'm trying to depict a few kilohertz as differences. So let me repeat again, few kilohertz on top of hundreds of megahertz. When I say few kilohertz, it could be as low as 1 kilohertz. In fact, it can be as low as 1 hertz on 500 megahertz. This is a very important point for everybody to understand and appreciate, which is what makes NMR a very powerful tool in studies of chemical or biomolecular entities. The mere fact that you are able to pick up a very, very small frequency on top of a very large frequency tells that you can differentiate chemical environments of spins that are in very similar environments, not same environment, but similar environments. So what do I mean by this? you're able to see that these two are methylene protons. The mere fact that this methylene proton is close to hydroxyl and this methylene proton is farther from hydroxyl and closer to a methyl group that has a plus I effect, you would realize that the chemical shifts of both methylene groups are not going to be identical. So this is what I mean to say, small subtle small differences in the local fields they experience will result in differences in their Larmor precession frequency. If the Larmor precession frequency is different, the energy difference is different, you could be able to pick up a time domain signal, which one Fourier transform will be able to pick up these frequencies. The major highlight I'm trying to make you understand, even a very small and a subtle difference of a hertz can be picked up, and this is not an exaggeration. In fact, nowadays spectrometers can distinguish something to the tune of 0.5 hertz or even 0.2 hertz if you do a process called shimming very well in low fields. So if you're able to get a 300 megahertz spectrometer, pretty sure you can make the shims so good that you can get a line shape of 0.25 hertz. And where do these numbers come from? These numbers come from the line width of a given measurement. Remember yesterday I told you that if T2 values are small, the transverse magnetization dies fast, which means the signal, instead of taking this long to exist, may die here itself. In which case, instead of getting a line that's sharp, you're going to get a broader line. Because the area under the curve has to be constant. If the line width increases, the intensity drops. And therefore, you're going to have lesser and lesser signal as you start becoming bigger and bigger in size. And therefore, these kind of values matter. If you set up your experiment well, then you can actually resolve resonances that are really close to each other, and making NMR a super powerful technique to see very, very small differences. So although we said it's an intrinsically insensitive technique, its power comes from highlighting subtle chemical environment differences that cannot be caught otherwise by any other technique. Remember, it's a non-invasive technique. You may always argue saying that X-ray crystallography could also get structural information with subtle differences that may exist. That is correct. But remember, at the end of it, your sample gets destroyed. There are pros and cons of every technique. Not every technique has all good stuff. NMR has some good stuff, some bad stuff. Same with X-ray crystallography. So generally, you tend to club different complementary techniques so as to gain the maximum effect out of it. Okay. So there were a few effects that I said that allows for the energy difference if being small, the good and bad of it. The bad of it is insensitivity. The good of it is that it's non-invasive. And one more aspect that I did not explain here is something called spontaneous emission. This is something I hope I would have mentioned when we started the course. When you have two energy levels, different processes happen when you shine light. There's going to be stimulated absorption, stimulated emission, and spontaneous emission, where the first two processes, which are stimulated, happens only when the light is present. On the other hand, the spontaneous emission happens even in the absence of light. And interestingly, spontaneous emission, think about emission process. That means it reduces the lifetime of the excited state. That means the spins are going to die very fast. Okay, interestingly, spontaneous emission is proportional to nu power 3 or nu power 2, I forget. Anyway, it goes with the frequency or the energy difference between the states. The energy difference between the states is less, the frequency is less. The frequency is less, spontaneous emission is less. If spontaneous emission is less, the lifetime of the excited state is longer. The lifetime of the excited state is longer. You can measure it for much longer time and therefore have less uncertainty in your energy. Remember, delta E times delta T is greater or equal to h cross by 2. Here we are trying to see how we can minimize the uncertainty in energy. And that can be minimized by making sure that you are able to measure delta T for as long as possible, right? So basically, things are inversely related to each other. Position and momentum, time and frequency. If you're able to measure time for a very long time, the frequency uncertainty reduces. Okay, so yet again, NMR benefits from the fact the lines are this sharp because of very low amount of spontaneous emission. Okay. And also we have understood the fact that the local chemical environment ends up deciding small chemical shift differences. And therefore, in each of this case, depending upon where things are, the peaks would come at different positions. Please be aware that the energy axis in NMR is given as ppm, which is defined as the chemical shift unit. So it will be delta would be something like your omega minus omega ref divided by omega naught times 10 power 6. This is largely because you have a reference standard, and many times the reference standard for organic molecules is set to tetramethylsilane, which is abbreviated as TMS. So TMS is set to something like 0 in ppm. The value or the unit ppm comes from the fact that you're taking differences of Larmor precession frequency of the spin of your interest. Let me put delta I here. This is the Larmor precession frequency of the spin of your interest. This is the Larmor precession frequency of your reference. Remember, if you take differences, something like 500.001 megahertz minus 500 megahertz, you're going to get value in kilohertz, right? And you want to divide it by the Larmor precession frequency. I'll come to it in a moment why we want to do this. So this is going to be in megahertz, this is going to be in kilohertz, and therefore maybe hertz to kilohertz, and therefore you multiply with the 10 power 6 so as to take the megahertz to a smaller value. So the parts per million, although it sounds like a concentration unit, is a relative energy unit. Most importantly, that factors out the effect of the B naught field. Why is this unit important? Independent of B naught fields used. What do I mean by this? Just for the sake of argument, imagine you're making a measurement in 200 megahertz and 500 megahertz. Realize that the B naught is different. Once again, for the sake of simplicity, I'll say, let's put it at 300 megahertz. So this is going to be 11.74 Tesla. And what is this going to be? 0.6 times 11.74. This is going to be 7.05 Tesla. Okay? The moment you have this, you realize that the gamma B naught, which is the Larmor precession frequency, which is omega naught, is going to be different for the same methyl spin in methanol. I hope now others are also able to see my screen.
Yes,
sir.
Okay, sorry for the delay. So the mere fact that the Larmor precession frequency is dependent on B naught for a given spin, you realize that the frequencies that you would end up measuring in terms of omega naught would be dependent on the field that you're measuring in. Okay, correct? And that's a problem. That means one person who measures on a 300 will cite a certain value. The person who's measuring the same thing on 500 will cite a different value. And that's going to cause confusion on people having to convert values here and there. And in order to minimize such confusions and also have a uniform standard of reporting chemical shifts, it helps to refer each of them with respect to the B naught that's being measured. And of course, the reference also helps you set a certain value at a certain relative energy. And it's your choice. Generally, tetramethylsilane is chosen because something called a shielding is the lowest for the tetramethylsilane in comparison to most of the CH bonds. There are always examples that go even less in value than TMS. This is just a reference that has been chosen. And therefore, you're able to see the two peaks that will come up for methanol would be well distinguished from each other. Magnetic field anisotropy, this is where AI also makes a mistake, it hallucinates, so don't take these things seriously. But what is the whole point I'm trying to drive here is that depending upon the OH bond that's being present, the same CH3OH could have differences that would come up in the gas phase versus liquid phase. In gas phase, more or less, you get a very sharp resonance because there is not much of solvation being present. Solvation is not being there, then the hydroxyl exchange becomes very less. On the other hand, the moment you have in the liquid state, then that proton is reasonably acidic enough where the exchanges can happen within each other, or let's say even you have a little bit of water being present where the proton could get exchanged with the solvent. This is chemical exchange. When that happens, once again, the line becomes quite broad because it affects the transverse relaxation rate. Imagine when you're making a measurement where you have CH3OH and H2O, the proton that was part of water might have exchanged with methyl, the hydroxyl proton in the methanol as you did the experiment. And this happens dynamically all the time because of chemistry. So due to which the uncertainty in the energy increases quite a bit. Okay, and this also causes a phase decoherence to happen. But overall, what I want to drive to you guys is that chemical shift is an anisotropic parameter, meaning that it's three-dimensional in nature. It is different across all axes for most of the cases. You cannot measure it in solution state because you average things out as tumbling happens all the time. On the other hand, if you want to measure the chemical shift anisotropy, you could potentially do it when you do a solid state NMR measurement where you have crystalline samples or even amorphous powder samples to measure some of these. Due to the lack of time, we can't go into the detail. There are definitions of what is delta sigma. I think it goes something like 3 minus 2 divided by 2 times sigma 1 or something of that sort. Okay, but I'm not going to go into details. Please take the textbook to take a look at it. Hopefully you understood how subtle chemical differences are highlighted given the fact that NMR has very high resolved lines because of large lifetimes of excited states. The large lifetimes of excited states comes from the fact that the spontaneous emission is low. Okay, and the phenomenon of phase coherence takes its own time to decohere. Since the T1, T2 times are longer due to many other parameters, you get very sharp resonances helping you resolve chemical shifts. Make sense? Now, in addition to this, the remaining 5 minutes, what I would like to highlight, I hope I've now given you an idea that if you have a sample like ethanol, each of that is going to have its own M naught, meaning this chemically different spin. Let's call it M naught dash and M naught double dash. And remember, they are going to be weighted by the number of protons that are going to be present. And each of them is going to experience its local spin environment that allows for chemical shift differences to get different number of resonances that you observe by getting the time domain signal. Okay, so in this case, what's going to happen? You're going to get a arithmetic sum of different frequencies in the time domain. This is a typical example of how you are able to listen to music in FM radio. You can imagine the 500 megahertz is the 100 megahertz you tune on your radio, and the song that you have, which has different frequencies, is what is embedded on top of another frequency. Do you follow? And what does your radio, how does your radio work? It cuts off, it picks up the 500 megahertz frequency and cuts that 500 megahertz off just to get your song frequency, be it any instrument or vocals that are being present. NMR works exactly the same way. The 500 megahertz is the carrier frequency, which allows for you to pick up the songs that are sung by atoms, literally, after you have excited them. Get that 500 megahertz, strip that 500 megahertz off, pick up the signal that's encrypted on top of it, where each one of them come up with their own frequency. And with the Fourier transformation, luckily Fourier transformation is linear and NMR is also a linear spectroscopic technique, meaning that the stimuli and the response have a linear relationship with one another. There are some spectroscopies which have a non-linear relationship, but luckily NMR is a linear spectroscopic technique where the stimuli and the response have a linear relationship, and therefore you would be able to get separate frequencies for them. So basically, what do I mean? You'll be getting the omega naught of CH3 plus delta function of omega naught of CH2 plus delta of omega of hydroxyl, just as a linear sum. So basically, finally, you'll get a spectrum where 3 lines are being there. I didn't do it properly. I was in a hurry. Just a moment. Where the CH3 will be like this. CH2 will be like this, and maybe hydroxyl will be like this. I'm just trying to give you an idea of 3:2:1 integral. So far, we have not said where the line broadening comes from. Okay, line broadening comes from a factor called relaxation, where in addition to the e power I omega t that you have, omega naught t that you have, you will also have a dampening function. Basically, this is exponential relaxation. And this comes up because of the phase decoherence that happens. And Bloch was able to model it with very simple first order rate kinetics, where the exp minus R2 times T, where R2 is nothing but 1 over T2 relaxation. Okay, the transverse R2 is the transverse relaxation rate, where T2 is the transverse relaxation time. Time and the rate are inversely related to one another, and therefore you are able to pick that up. Okay, and the line width would come up once you have the relaxation component being there. Somebody had a question here. Okay, yes. So each of the spin ends up experiencing its own local environment. And since there are 3 identical protons, the length of the magnetization, bulk magnetization also increases, increasing its sensitivity. If you end up exciting it and detecting, like what we discussed yesterday, you're going to have signal that comes up in the form of time domain free induction decay. And you're going to have 3 free induction decays that are going to be added on top of each other because the linear response for methyl, methylene, and hydroxyl, which when you Fourier transform, you would be able to get multiple resonances based on their unique chemical environment. Okay, is that clear? Any other questions from others? Please unmute and speak up. We have only about 2 minutes to wrap up. So therefore, due to relaxation, each of them would end up getting broader. But remember, the relaxation rate for hydroxyl will not be equal to the relaxation rate of methyl, or for that matter, the methylene group. They have their own unique relaxation rate. That's a combination of multiple factors, including something called exchange factor, meaning that any conformational exchanges that happen, meaning that if a bond is moving in a certain direction, has an interaction, that will all end up perturbing the REX, which in turn gets embedded on R2. Okay, and if it gets embedded on R2, it gets its influence on T2, and therefore line widths would be different. So overall, I hope I have been able to convince you on the fact that when you have a molecule with different nuclear spins with a unique electronic environment, we embed the subtle differences in the frequencies on the larger Lama precession frequency. And after we get the time domain signal, we'd be able to Fourier transform and remove the Larmor precession frequency based information and only pick up the subtle differences that arrive, that come up due to the differences in electronic environments on the spin. Make sense? Okay, any other questions?
Sir, why are you multiplying exponential e to the power I omega t with this? Like, what
it
are you trying to
happens-
get?
I'm not multiplying. We are just trying to model. So good question. I should have made it a little more clear. If you realize here, if you take the top of the signal, you realize an exponential decay happens. Or rather, a first order rate based decay happens, which we'll see after Bloch equations. This
Yes,
is related to something like, I'm sure you'd have solved this kind of minus dA by dt is given as the rate, I mean, how much of concentration of A is present. There's the same thing. If you end up modeling the relaxation as a first order rate kinetics, the e power minus R2t comes by itself. Okay?
yes, sir.
Any
And
other
the
questions? Yes.
e to the power I omega not t is
Okay.
that's the RF pulse we're applying.
All I'm trying to say is that the signal has a functional form that we would be measuring as a cos and the sine components, which put together you'll have a complex component of e power I omega naught t. On top of this, this is an oscillation, meaning that this will keep on going forever. On the other hand, the relaxation also happens. So both put together gives you a signal, which is the FID. All right. Any other questions? Priyadarshini, Deeptanu, Puneet?
No, sir.
Okay. Any from here? Okay. Thank you, guys.